Hello, you're very welcome to this video called Keeping an Eye on the Planes. I'm Seamus Ballieu, and this video looks at the equations of planes and systems. The equations are mainly in 3 dimensions. This video is for second year electronics students at Dundalk Institute of Technology. So we'll make a start. First thing we'd like to do is to look at the idea of points in 3 dimensions. And sometimes it can be a wee bit difficult just to visualize what's going on in 3 dimensions. So what we've done here is we've taken a photograph of a 3-dimensional situation. So here we've got the x-axis, positive direction, negative direction there. We have the y-axis, positive direction, and the negative direction on the y-axis. So that sheet of paper was laid on a table. So that's on the flat surface on the top of a table. Then this marker here represents the z-axis, the positive z-axis, and the negative z-axis would go under the table. So this here roughly has a length of 3 units, and that's 3 units there, and we're taking the marker to be a height of 3 units roughly. It's hard to see it there in the 3 dimensions. So for example, if we asked you to locate the point 2, 1, 3, so 2 represents the x value, so that's 2 on the x value, so you come in there, so the point is going to be vertically up from there. There's 1 on the y-axis, so the point is going to be vertically up from there, so somewhere along there, and then eventually the 3 decides the position on the z-axis as to which we'll position the point. So we're operating from that 2, 1 on the 2 dimensions, and then the height of the marker is 3, so we just come across here. So that point, the top of that marker, is 3 units high on the z-axis. So that's the point 2, 1, 3. So here we look at an example of a plane. A plane is a flat sheet of paper. It's a flat surface, not bent. So sheet of paper might just look a wee bit bent there. So that sheet of paper has points on it, and we can identify the points in 3 dimensions. So here we're using our previous scheme. So that plane goes through that point there, 1, 0, 0. It's 1 on the x, 0 on the y, and 0 on the z. It also goes through the point 0, 0, 3. It touches the top of the marker. It kind of folds in. And it's also on the point 0, 2, 1. And that point lies on the y-axis. And then we've identified some other points that belong to the plane. So the equation of the plane is 6x plus 3y plus 2z equals 6. And you can verify that the various points lie on the plane. So for example, substitute the 0 in for x, 0 in for y. 2 times 3 is 6. So we've checked that point lies on the plane. Likewise, 0, 2, 0. 3 2s are 6 and the other values are 0. So it's 6 again. And here's the point here on the surface of the table. But it's over half on the x and it's up 1 unit on the y. We'll see it a little bit more clearly in a minute. And it's 0 on the z. So the point 0.510 also lies on that plane. 6 times 0.5 is 3, plus 3 ones are 3, plus 0 equals 6. And then this point here on the plane, okay, those points are kind of on the plane, but they're touching the surface of the table. And the plane goes underneath the table. The plane carries on underneath the table, and it carries out in this direction here, that direction. So a plane has infinite direction, infinite size. So we're just representing a section of the plane, really. So this is another view again, only this point here is a little bit more clear from a slightly different angle. So there's 0.5 on the x, 1 on the y, and 0 on the z. And again, we said that the z-axis, the marker, has a height of 3 units. So that point there is 0, 0, 3, and it lies on the plane. And the point 1, 1, 1 is also on the plane. So later on, we're going to show you how to work out that equation. Okay, so now we're going to show you various combinations of sets of 3 planes. So this situation here has 3 planes, as you see. One plane there, one kind of coming out, the blue edge there, and the one with the green edge. So those 3 planes have a unique point of intersection. and that's how we draw the situation in 2 dimensions. It's like doing a cross section. So that plane there with the black surround the lines is shown there on the plane of the board as well, and then the green plane, kind of the section is going in, and the one with the blue, so that's that blue line along there, so it's the blue lined plane. This setup here has 3 planes again, only this time we have what we call a prism of 3 planes with no common point of intersection. And again, we do a cross section, so it's easy to visualize it in 3 dimensions. Those planes only meet in pairs, so those 2 planes meet along a line there, the one with the red edge and the orange edge meet along that line there. So those planes meet along a line, but only 2 of them meet at a time. The 3 of them never meet, so there's no common point of intersection. These 3 planes are what we call a pencil of planes. They have an infinite number of intersection points. So we've got the one with the purple edge, the green edge, and the blue edge. And you can see that the meet down along there, there's a whole line of points. There's an infinite number of points. So that line is an infinite length. And there are an infinite number of points of intersection of those 3 planes, and the form what we call a pencil of planes. So let's look at an example of Kirchhoff's law from electronics. And this system of 3 by 3 equations will have a unique point of intersection. So that represents 3 planes that have a unique point of intersection. The first graphic that we showed you there. So I1 plus 2I2 plus 4I3 equals 85 milliamps. Likewise in the second equation and the third equation. And we could also do those in X, Y, and Z accordingly. So we're going to solve this system using Gaussian elimination. And you can check out the earlier video on the details of the Gaussian elimination. So again, as a brief reminder, in the Gaussian elimination, we look for this situation here. We put the information into what we call augmented matrix form, 1, 1, 1, 2, 3, 6, 4, 6, 10, and then the figures on the right hand side, 85, 126, 215. So we aim to get zeros in these positions. So the 0 here will be row 2 minus row 1, 1 minus 1, 3 minus 2 is 1, 6 minus 4 is 2. Then we do the 126, take away 85. Likewise row 3, and we end up with the following situation. 0, 1, 2, 126 take away 85 is 41. Likewise row 3 minus row 1, 6 minus 2 is 4, 10 minus 4 is 6, 215 minus 85 is 130. And we carry on with the Gaussian elimination. We have our 1 in that position there, so that's good. And now we're going to do row 3 take away 4 row 2. So we end up with 0 minus 0, 4 minus 4 1s, 0, 6 minus 4 2s, 6 minus 8 is minus 2, 130 minus 4 by 41, so it's 130 minus 164, which is minus 34, and we're nearly there now in our Gaussian elimination. We want to get that situation there, so we divide that row 3 by minus 2, and we get 0, 0, 1, and 17. And now we can extract out the corresponding equations. So that first equation is the same as the original equation that we had. So extracting the equations then, I1 plus 2I2 plus 4I3 is 85. I2 plus 2I2 equals 41. I3 equals 17. So we know what the value of I3 is. Substitute the 17 back in for I3 on that second equation. 2 17s are 34. So I2 plus 34 is 41, I2 is 7, and then substitute the 7 back in for I2, 17 for I3, so we get I1 plus 2 7s are 14, plus 4 17s are 68, so 68 and 14 is 82, so I1 plus 82 is 85, so I1 is equal to 3. So again, just to summarize, we have I1 equals 3, I2 is 7, I3 is 17, and we can check our answers. If you fill the 3, 7 and 17 into these equations, you end up getting what's on the right hand side. So on that first one there, 3 plus 2 7s is 14, so that's 17, plus 4I3, that's 4 17s, which is 68, and 68 and 17 is 85. So the I1, I2, I3 satisfy that first equation there, and likewise you can check the other two equations. So moving on to another example, we've got three planes again, and the question is, which of the three situations does this one look like? So again, we put the information into augmented matrix form and we solve using Gaussian elimination. So hopefully you're used to the Gaussian elimination now. So we do row 2, take away 2, row 1. So that gives us 0. 11 minus 2 5s is 1. 1 minus 2 3s, so that's 1 plus 6, which is 7. 9 minus 2 6s, 9 minus 12 is minus 3. Row 3, that's minus 2 there. So it's row 3 plus 2 row 1. Now don't be tempted to do row 3 and plus row 2. That might lead to some confusion. You always go back to the pivot. So minus 2 plus 2 1s is 0. Minus 9 plus 2 5s. Minus 9 plus 2 5s. Minus 9 plus 10, which is 1. 13 plus 2 minus 3s. 13 minus 6 is 7. Minus 5 plus 12 is 7. So we're kind of gradually getting there. Now we like to get a 0 into this position. And look what happens this time. Row 3 minus row 2. So we get 1 minus 1 is 0. 7 minus 7 is 0. 7 minus minus 3 is 10. So we end up with a situation we haven't seen before. So we extract out the equations. What do the equations look like? So we put the equations into the augmented matrix form. Now that we got to the end, we extract them back out. First equation is the same. Second equation is y plus 7z equals minus 3. But look what happens in the third one. 0 times x plus 0 times y plus 0 times z is all equal to 0. So 0 equals 10. Now you know this is not a true statement. It's inconsistent. So that means we've got no point of intersection this time. Those three planes don't meet. We attempted to find out the point of intersection, but there is none. And that's given by the answer. And there's your diagram there. So we have a prism of planes that meet in pairs, but they never meet at the same time. So example 5. So again, putting the three planes into augmented matrix form and solving using the Gaussian elimination. Row 2 minus row 1. So 0. 3 minus 2 is 1. 5 minus 3 is 2. 20 minus 12 is 8. Row 3 minus 2 row 1. So 2 minus 2 1 0. 3 minus 2 2s. 3 minus 4 is minus 1. 4 minus 2 3s. 4 minus 6 is minus 2. 16 minus 2 12s. 16 minus 24 is minus 8. So we got the 1 there. So we want to get a 0 in that position. So it'll be row 3 plus row 2. And look what happens this time. We get zeros going all the way across. Extract out the equations. X plus 2y plus 3z equals 12. Second equation, x plus 2z equals 8. And the last one is 0 equals 0. And that means we've got a pencil of planes. So 0 equals 0, so we can discard that. That's a true statement, but it's not giving us any new information. So we look at the two equations that we have. X plus 2y plus 3z equals 12. Y plus 2z equals 8. So we can actually let z equal any number we like. When you've got a unique solution, you always end up with z equals some number, z equals 3 or z equals 7. And then you feed back into that second equation to get y. And then you feed your z and y back into the first one to get x. So it's a unique solution. But here we can pick z to be any number we like. Once you pick z, you can feed it back into the equations and you get one particular point. But then you could pick a different z, feed it back in, and you get another point. So let's see how that works. So for example, let z equal 5. We can let z equal any number we like. So if z is 5, what's the corresponding y? Y plus 2 5s is 10 equals 8. So y equals minus 2. What's the corresponding x value? X plus 2y. So x plus 2 times minus 2. So that'll be minus 4. Plus 3 times 5 is 15. So overall that's 11. So x plus 11 equals 12. X equals 1. So this is a point in 3 dimensions. that falls on those three planes that we were looking at in the question. So x is 1, y is minus 2, z is equal to 5. But this is a pencil of planes, so there's a whole line of points that make up where the planes intersect. What would happen if we let z equal minus 1? Just picking these numbers off the top of my head. Z equals minus 1. So again, feed the minus 1 into the second equation. Y plus 2 times minus 1 equals 8. So that's y minus 2 equals 8. Y equals 10. So then feed the 10 and the minus 1 back into the top equation. 10 in for y, minus 1 for z. So x plus 20 minus 3, that'll be x plus 17. X plus 17 is minus 12. So x equals minus 5. So x is minus 5, y is 10, z is minus 1. So we've seen two examples where you can pick particular numbers for the z value and you can come up with points that lie on the three planes. So in general, we're going to come up with a solution now. We let z equal t, that's any number, and then we feed the t back in just like we fed in the numbers. So how does that work? So y plus 2t equals 8, y equals minus 2t plus 8. And now we feed that y into the 2y there and feed the z equals t in there. So how will that work? So we get x plus 2 times y, and the y is minus 2 plus 8, minus 2t plus 8, divided by 2, plus 3 times t equals 12. So we tidy up that equation. X minus 4t plus 2 8s are 16, plus 3t equals 12. And then we have minus 4t and 3t gives us minus t. So x minus t plus 16 equals 12. X equals, add t to both sides, and we get t, and take 16 away from both sides. X equals t minus 4. So piecing all that together, x is equal to t minus 4, y is minus 2t plus 8, z equals t. And t can be any value you like. T can be any value you like. What would happen if we had let t equal 5? We get 5 minus 4 is 1, minus 10 and 8, minus 10 plus 8 is minus 2, and if z is equal to t, and we're saying t is 5, so z is equal to 5. So that's one of the points, and that's one of the points we had earlier on. Likewise, if we do t equals minus 1 and minus 4 is minus 5. Minus 2 by minus 1 gives plus 2. 2 and 8 is 10. That's the y value. And then z is equal to minus 1. And that's the other point that we had. But you could pick any t value you like. What would happen if we pick t equals 0 over the corresponding point b? It would be minus 4, 8, and 0. Now we're back to the plane that we had at the beginning of the video. We're going to try and find the equation of this plane. And we're going to take 3 points that lie on the plane. The point 0 to 0, the point 0, 0.5, comma 1, comma 0, that's that point there. The plane goes under the table, but that point is actually on it. And the point 0.5, 0.5, 0.75. So that's the point there. That's the point highlighted on the plane. It's kind of up a wee bit, just hard to sort of see it in the 3 dimensions. So that's a point that's on the plane. So we take those 3 points and we do our business. So the equation of that plane is some number a times x plus some number b times y plus some number c times z equals d. So what we're going to do is we substitute those points in for x, y, and z. Sorry, we're going to substitute each point in turn. That's the x value. 0.5 goes in for x, 1 goes in for y, 0 goes in for z. Likewise for the next one. So how does that look when we do that? So it's 0.5 times a plus b times 1 plus 0 times c, that's why there's no c there, equals d. Then do the second point, 0 plus 2b plus 0, so 2b equals d. And the third one, 0.5a, so 0.5 in for x, 0.5 in for y, 0.75 in for z, and we get 0.5a plus 0.5b plus 0.75c equals d. So we're used to solving a system of 3 by 3 equations, only they usually involved x, y, and z. Here they involve the letters a, b, c, and we're just regarding d as a number, so no problem there. Put it into matrix form, usual. So This system of equations that we've come up with can now be put into augmented matrix form, which we have here. And now we've performed the Gaussian elimination, and we aim to get the ones in the diagonal and the zeros. So we go row 1 multiplied by 2, or row 1 divided by 0.5. That will ensure we get a 1 in that position there. We can do a few steps here together because it's fairly easy. Row 2 divided by 2, and we want to get a 0 in that position there. So we can take a wee bit of a shortcut. Because our 2.5s are the same, we can simply say row 3 minus row 1. And that'll give you the 0 there. So we end up with 1, 2, 0, 2 times d dividing by 0.5 or multiplying by the 2, 0, 1, 0, 0.5d or a half d, 0.5 minus 0.5 is 0, 0.5 minus 1 minus 0.5, 0.75, and d minus d is 0. So then the next operation is we want to get a 0 in that position there. So it's row 3 plus a half row 2. So that'll give you the 0 there. That'll still be 0.75, and half of 0.5d will be 0.25d or a quarter d. So let's take a look at that. So that's just the previous slide, and that gives us what we said, 0, 0, 0.75, 0.25d, and we want to get a 1 in that position, and then we'll be done. The Gaussian elimination bit complete. R3 divided by 0.75, so 0, 0, 1, 0.25 divided by 0.75 is a third, d over 3, or 0.33d. So we end up with that situation. And now we can extract out our equations a, b, c, and in terms of d. So the equations look like a plus 2b is 2d, b is equal to 0.5d, c is equal to d over 3, or 0.33d. So at this situation now, what have we got? We have d some number on the left hand side, and we can actually let d equal any number we like. Now you might find this a little bit hard to understand. D is sort of an independent variable, and the a, b, c depend on it. So for the moment, we'll let d equal 6. 6 is a good number, and we'll come back and we'll explain this in a little bit more detail later on. So for the moment, we'll just let d equal 6. You can let d equal any number you like. Well, any non-zero number, let's say. So a plus 2b equals, and because we're letting d equal 6, 2d is equal to 12. So a plus 2b is equal to 12. B is equal to 0.5d. Again, we're saying d is 6. So b is half of 6, which is 3. b equals 3. C is equal to d over 3. So c is equal to 6 over 3. So c is equal to 2. Now we know that a plus 2b is equal to 12. B is 3. So 2 3s are 6. So a plus 6 is 12. A is also equal to 6. So let's summarize that information. We have a is 6, b is 3, c is 2, and d is 6. We chose 6 to be the value for d. And then we got a, b, and c. So the equation of the plane that we set out to look was ax plus by plus cz equals d, and carrying forward our values a, b, c, and d. The equation of the plane is now 6x plus 3y plus 3z equals 6. That's the equation of the plane. Now, do you remember we said a few minutes ago that you could let d be equal to any number you like? So we'll choose another value for d, and let's see what happens this time. D equals 12 is still a reasonably nice number, but you can pick any number you like. But let's pick a different number. We picked d in the previous time. So this time we're letting d equal 12. A plus 2b is equal to 2d. So a plus 2b is equal to 24 this time. B is equal to half d, 0.5d. So b is half 12, which is 6. C is d over 3. 12 over 3 is 4. C equals 4. So just looking back then, if b is 6, 2 6s are 12. A plus 12 is 24. So a is equal to 12, and we chose d to be equal to 12. So substitute those values back into the a, b, c, and d, and what do you notice? We get 12x plus 6y plus 4z equals 12. So that's the new equation that we got when we picked the value of d. But what do you notice? There's the equation there. If you divide that equation across by 2, what happens? You get 6x plus 3y plus 2z equals 6. So no matter which value of d you get, you always end up by showing that it's an equivalent equation to this plane here. So that's the equation of the plane. So there's the original plane that we showed early on, and that's the equation that we got. We gave you that equation early on, but now you can see where the equation came from. We use these 3 points to get the equation, and you can check your answer. So is 0, 2, 0 part of that plane? So fill 0 in for x, 2 for y, 3 2s are 6 plus 0 equals 6. So that point is on the plane. And likewise, you can substitute that point in, 0.5 for x, 0.5 for y, 0.75 for z, and you can see that you get 6 as well. And likewise with the third point. Now, there were some other points in that plane that we didn't use in the calculating of the equation of the plane. But those points were 0, 0, 3, 1, 0, 0, and you can check those points are on the plane. There are millions of points on the plane, an infinite number of points. We only picked a few, and you could check that various points are on the plane. So I hope you enjoyed the video, and we look forward to seeing you the next time. Thank you very much.